All right, so I'm making a quick video to help you guys make a cheat sheet for your next test. If you haven't noticed already, this section, this chapter is crazy. There are so many different details for you to deal with that I feel like I need to help you make this cheat sheet, help you make a checklist essentially that would make sure that you're looking at all the things that you're supposed to look at. Make sure you take care of all those little details and keep them all straight. So, the idea is that on this test, I actually would let you use your notes, but your notes aren't always helpful. You need to know what to look for and what things to do so that you can actually get things accomplished. So, again, I'm just trying to help you out a little bit. So, I want you to fill out a note card with this set of guidelines with these things that I'm going to put in this video. And then I want you to try and use that on a review worksheet and see if it helps at all, right? If not, we'll work more at it because obviously we're going to have to get it figured out. But there are just little details that we keep forgetting and we don't always look at that we need to get straightened out before we can take a test. So again, just going to run through a list of things to do, right? Number one on this list, right? The very first thing that you need to focus on every time, and it's what's killing us sometimes, is that we have to know our charges. You have to know charges for all of those polyatomic ions for any given metal, non-metal that could be in a compound, right? Because you have to have the appropriate charges so that you can have the right formula, because it's not good enough to just say, okay, it's magnesium hydroxide, right? I need to know that there should actually be 2 hydroxides per magnesium, that I have to use parentheses, all those things, or else nothing else works, right? I can't do the reaction. I can't take care of the things that I need to take care of if I don't have these details right. So it's really, really important that we get our formulas right. So at the end of the day, it might be important that you put all of those charges on the back of this note card, right? Put all of those polyatomic ions that you might need. I mean, most of the metals that you need to know, like magnesium, you can just look at your periodic table and you know what the charge is. But in terms of those polyatomic ions that we still don't know, you might want to put those in the back of this cheat sheet. So again, always, always, always check your charges before you create that formula so that you can get everything to work. Number 2 on the list, right? When you're asked to write out these equations, these reactions, sometimes it's not a compound. Sometimes it's an individual element, right? But you always need to look out for those elements that I told you are going to be diatomic, right? You have to know again that hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, iodine, all those halogens, right? You need to know that those elements have to have those little 2s, right? They're always diatomic. They're more stable with 2 atoms bonded together than separately. Otherwise, any other element, unless I tell you, shouldn't look like that. They should always be singular. So, again, on your quiz that you were doing, I actually told you that sometimes sulfur has a little 8, right? But I'd have to tell you that, right? That it's in that octet. So, always look out for hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, iodine. Those should always be diatomic, right? So again, just like before, if you don't have those little numbers correct, if you can't get formulas right, if you don't know what things should be diatomic, you're never going to be able to balance these equations and get the right things going. So you just have to pay attention to those details every time. Number 3 on the list of things to know. I keep saying this, but I don't know if the way that I say it doesn't help you guys, but I keep talking about how your formulas have to be correct. You have to have that magnesium hydroxide correct. You have to have hydrogen being diatomic, bromine is diatomic, right? You have to have the formulas correct first for everything that's in your reaction before you can balance, right? Now, yeah, I say a lot of times that you need 2 hydroxides to balance out with the magnesium, but when I say balance in context, right, when I'm talking about balancing an equation, I'm always talking about coefficients, right? So I want you to take care of those formulas first. Make sure you have every little detail right. Magnesium hydroxide, hydrogen's diatomic, right? Then I want you to balance the equation overall using coefficients, right? Meaning that I might end up putting a little 2 in front of this magnesium hydroxide, but that 2 is a coefficient that I added to make sure that everything balanced. So to make sure I had the same number of everything on both sides of the equation, right? Whereas this little 2 in the formula itself is different, right? I didn't put that there so that the 2 sides of the equation would balance. I put that there because it has to be there. Magnesium has a +2 charge. So you have to have 2 hydroxides to go with that, to make that formula itself neutral, to make it balanced. Whereas the big number balances the equation as a whole. So I keep saying it that way. I keep telling you guys that you should worry about your little numbers first, then worry about your big numbers, right? So if I say little numbers before big numbers, I mean when we write out an equation, when I tell you hydrogen plus bromine can synthesize hydrobromic acid, right? This already looks like it's balanced, but that's because I forgot to put this little 2 on this hydrogen. That's because I forgot to put a little 2 on this bromine. You have to have little numbers correct first. Little numbers meaning these subscript 2s, before I could possibly balance the equation appropriately, right? Before I could put in a big number that I probably need right here, I'm going to need a 2 in front of that hydrobromic acid to make this balance overall. So again, there's a difference between big numbers, those coefficients that I'm using to balance both sides of the equation, and the little numbers that are just details that we're supposed to know. So always get the little numbers first before you do your big numbers. So if you can get through 1, 2, and 3, that'll solve like 90% of our problems, right? Then from there are more details that we have to deal with. Again, I'm really trying to talk about stuff that are not, they're in your notes, but you don't always think of these things, right? So number 4 on the list, right? In section 1, we talked about reaction indicators. We talked about symbols that are in our reactions, our equations, right? And some kind of important ones that we keep forgetting to do, right? First and foremost, right, there are 4 different indicators of reaction. I need to know that I might see bubbles, right? I might see a color change. Use this symbol. I might see energy released as light or heat, right? And I might see a precipitate, right? So I ask you questions about those things all the time, and we are always confused, like, well, what do you mean by that, right? So again, if I'm looking at an equation that's already written for me, I might see certain symbols that'll give me hints, right? I might see an up arrow that tells me that there are bubbles, right, that are formed in that solution, in that liquid, right? I might see a down arrow to tell me that there's precipitate formed, right? If I'm actually watching the reaction, literally, I could see those things forming, right? But in the equations themselves, sometimes I can indicate that that's happening. It's harder to indicate that energy is being released. You can't see the light coming out of the reaction itself, right? And I can't draw that in the formula necessarily. And I can't draw the color changes either, because for your purposes, copper looks like copper. So whether it's a +2 in an equation that looks like, or a formula that looks like this, versus on the other side being slightly different because it's a +1, right? In real life, you'd know that this happened because this copper ion is blue, right? Whereas the other copper ion is kind of a reddish brown color. So it's obvious that there's a change. You just might not be able to tell looking at an equation, right? So color change energies, we don't usually see those unless we're literally watching the reaction. But bubbles and precipitates pop up all the time, and it confuses us, and I don't know why, right? So again, lots of different symbols that you can see. If I have an equation, A plus B gives me C and D. I don't really care what these things are. I'm just making something up on the spot, right? If A and B are aqueous, that means I have a solution. Those things are dissolved in water. And so when I put like an up arrow over here, that means that C was formed and it's a gas and it's bubbling out of that liquid, right? If I put a down arrow on D, that means that it's a solid that was formed in that liquid and it's sinking to the bottom. So I need you guys to, for once, right, what's up on the board, write down those different labels that I might use: solid, liquid, gas, aqueous. We need to know those symbols, and that a solid is a precipitate, right? The aqueous means that it's soluble. That a gas may bubble out of solution, right? I don't have a special mark for a liquid because a liquid inside of a liquid just mixes with that liquid, right? It might actually be considered soluble to a certain extent, right? But on the quiz, when I was telling you that nitrates are soluble, that'd be like me telling you that B is soluble, right? So that means that it's aqueous. So it can't possibly be the precipitate, because a precipitate, by definition, is not soluble. It's falling out of solution. It's a solid that forms in that solution. So you should be able to use that information to get what you need. So again, we're a little all over the place here, but know your 4 indicators of reactions and know symbols for those things and understand what a precipitate is, right? When bubbles may form, right? And know to look for those symbols, an up arrow or a down arrow, to indicate those things. Right? 5, right? Just got a couple more things you can power through, right? 5 is all about reaction types. When it comes down to it, you're going to have to predict products of reactions, and you're going to need to know the difference between our different kinds of reactions: synthesis, decomp, combustion, single, double displacement, right? So I had you write these things down a long time ago, but you don't have them readily available all the time. Put them on this cheat sheet and you'll know what you need to look for. So synthesis. Those reactions always have one product. So that means you would have A, B, and they make C. C is a product. There's only one product. That's a synthesis reaction. Whereas decomp always has one reactant. So if I flip that, if C was broken down into its parts, A and B, that would be a decomposition reaction. So if you see one reactant, it's a decomp. If you see one product, it's a synthesis. understand the difference. Combustion is your next one to look at, right? And I like to do that one next because sometimes combustion can look like a synthesis, right? Sometimes these things can overlap. But the one thing that will always tell you what's happening is combustion always has oxygen in it. So if you see oxygen as a reactant, it's definitely a combustion, right? For our purposes, it's definitely going to be a combustion. So even if there was one product, it's still a combustion because you saw oxygen as a reactant. And then you have single and double displacements. And I told you what to look for there. If it's single displacement, you should have two reactants, two products, and there should be a single element on both sides of the equation. So know to look for single elements as opposed to compounds, right? Because that's what you look for in double displacement. You should have two reactants and two products, but they're all compounds. Again, I've said for both of these that you need to see two reactants, two products. If there was ever one reactant or one product, you automatically go back to synthesis or decomp. So as soon as you see two reactants, two products, it kind of had to be single, double, or combustion, actually. And as soon as you've eliminated combustion because of the oxygen, the only things left to look for is, are there single elements or not, right? So those last two should be taken care of by finding the one with the single element. The other one's probably a double displacement. Once you know what kind of reaction it is, then you go to your notes, find the right kind of reaction, and see if you can model from there. But again, no matter what, once you get this done and you're trying to predict your products, you need to refer back to 1 through 3, right? You need to make sure you start making compounds that have correct formulas, and everything that's diatomic is diatomic like it's supposed to be, so you can get the little numbers right before you can get the big numbers right. So again, it all comes back down to, do you know that stuff or not? Can you differentiate between when something needs that little number and when it doesn't, right? But if you can get your little numbers right, the big numbers take care of themselves. Right? That's basically how that works. So again, we have to know our reaction types so we can find what we need. Finally, last thing I'm going to go through. I'm sorry if this video is getting a little bit long, but we need to be able to deal with an activity series. Now, you only do that if you're told to do that. I told you on the quiz, you don't need to use an activity series every time. Most of the time, I just intend you to know that that reaction is going to work and go with it. But when I tell you that this group, you need to use your activity series, make sure that you know how that works. You're supposed to find your examples that are going to be non-reactive, that are actually going to be no reactions. So look for those. I'll tell you how many there are because I always do that, but don't force it. I told you how many there were so you could be comfortable when you're done if you happen to have that many to begin with. I didn't tell you to go ahead and guess and make sure that you have 4, right? If you don't know that there should be a no reaction, then it's better for you to ignore that altogether than to even worry about it. You're just going to miss more points if you try and force a no reaction when it shouldn't be a no reaction. So if anything, just predict products for everything, right? Because again, at the end of the day, even if you find the right no reactions, Most of them, you have to predict products. And when you're predicting products, again, go back to rules 1 through 3, right? Make sure you get the little numbers first, and then worry about your big numbers. I keep harping on that, but it's a big deal, right? If you don't get those little details right, you're gonna struggle. But again, always check your activity series. Remember, there are certain reactions. Sometimes you're reacting with water. If you see that water is a liquid, it's not going to be hot enough to react with that second group of elements, right? That automatically tells you that you don't have a hot enough temperature. But as soon as I see that it's a gas, water can react with magnesium. It can react with aluminum. Because as soon as I see that it's a gas, I actually already know that my temperature is at least 100 degrees Celsius. I know that water is really hot, that it's a gas, it's steam, right? Any of these things, those are what you look for. If it's a steam, if it's in a gas state, or it says 100 degrees Celsius, any of those three things can tell you that it'll work for group 2 elements, for that second group of active elements. But if you're in that top group, it doesn't matter what it says. As long as there's water, it'll work, right? Otherwise, if something's going to react with an acid, right? Remember, acids are just H anything that's not water, right? But if it's going to react with an acid, it has to be higher than hydrogen on the list. So since cobalt is higher than hydrogen, but copper isn't, copper cannot react with an acid, but cobalt can, right? That's the whole idea. Otherwise, lots of things can oxidize. So most of the elements can actually react with oxygen to give you products. Again, these could be considered combustion reactions, right? If a lot of energy is being released, it would be a combustion reaction. But they're definitely synthesis. But just because there's a little 2 here doesn't mean that when I react sodium and oxygen together, that I'm going to get a little 2 on my oxygen over here, because in reality, I need a little 2 right here next to my sodium. So again, get your little numbers right, then worry about your big numbers. And again, I just screwed that up because I worried about the wrong big number first. I have to have 2 oxygens, and then it's actually 4 sodiums. So when I do one of those oxidations, right, just like always, make sure you get those details right. But the only things that won't oxidize are those things at the bottom of the list. You can pretty much bet that if you see silver, platinum, or gold, they're not going to do anything, right? Silver could replace gold, but silver's not going to do any of the reactions we talked about, generally speaking. Otherwise, remember, you also have your halogen series, right? That's where it's important to understand that, fluorine can pretty much replace anything. But again, this is where we have little number issues again, because you have to know that halogens are diatomic. And when I throw that fluorine in place of a chlorine, oh, look, there's no 2 anymore, because the potassium has a +1 and the fluoride's a -1. But, oh, wait, I have a 2 on the chlorine now? You got to know how to balance these things appropriately. And again, I put examples in your notes for a reason, so you could see the different ways that it might balance. But you got to figure out what the charge of that potassium is first, or you're never going to know, right? Because it's going to be a completely different story if that was a magnesium. Because if it was a magnesium chloride, I actually would have a little 2 in that formula to begin with. So this one's simpler and it's more convenient. But again, as we've gone through this, you've discovered that just because it's convenient doesn't mean it's right. And it's rarely right if it's convenient. So be careful. Otherwise, again, if you're not asked to use an activity series, don't worry about it. Because again, even if at the end of the day you never figured out how to do an activity series, if you can predict products and do it every time, you're probably going to pass. finding the no reactions isn't as big of a deal as you think it is, right? And if nothing else, ask me a million questions and you'll figure out which ones are no reaction. So again, sorry for making this video really long, but this is something we need to do correctly and we're struggling. So hopefully this helps, and take care of that